And now we're going to introduce our elegant solution. It's called a semaphore. And I've talked about signaling. Well, you can see, okay, so a guy with signal flags. And so we're going to come up with a way, a very elegant technique to allow the producer and the consumer to communicate about the state of what's in the buffer and what's not. So we introduce a new data type called a semaphore. You can think of it at some level as an integer. It's just a number. It goes up and down. It gets incremented and decremented. But we're not allowed to use it as an integer. We're not allowed to use plus and minus operations on it or look at it directly. The semaphore, there's only two operations you can do on a semaphore. One is called wait, and the other is called signal. Right, and it's tempting to solve various sorts of problems we might give you by thinking of it as an integer sometimes and dumping a 0 into it or manipulating it as if it's an integer. You shouldn't do that. The only way we can ever touch any of the value in the semaphore is either using the wait operation or the signal operation. So wait is pretty simple. What wait does is that it basically waits until the semaphore is non-zero, has a non-zero value, and then it decrements and returns. So when if a procedure calls wait, it doesn't necessarily, wait may not return right away. It will stall inside of the wait, waiting until the semaphore is non-zero. And when it is, it will decrement it and return. Everybody got that? Okay, and signal is correspondingly simple. Signal simply increments the semaphore. So it adds 1 to the semaphore. But again, remember that we want to make sure that we always access the semaphore using wait and signal. And there's a very good technical reason for that, which will become apparent in just a moment. Yes?
So you say wait semaphore 2, so it just returns semaphore now is equal to 1, and it doesn't make anything with it?
Yeah, so if in fact it can decrement it right away and return right away, it will. And we'll see that in operation too, right? So remember, the argument to the semaphore, the argument to wait and signal is the name of a semaphore, and you should think of the semaphore as having an integer value. Okay, in this case, you can see we initialized it to k, and so what we're doing is that we're managing a resource that has sort of k parts to it, and that'll become more obvious. But technically, if we initialize this to k, what we're doing is the semantics of wait and signal implement the precedent constraints that we're talking about. In other words, that the way the semaphore works is that the ith signal has to happen before the ith plus kth wait. And that's maybe a little abstract. We'll have a good practical example, and it'll become much more clear what's happening there. Okay, so the thing you should keep in mind is this is a data type that has a constrained set of operations, wait and signal. You should understand the semantics of wait. If it's non-zero, if it's greater than 0, decrement it and return. If it's not greater than 0, wait, okay, until it is, and then decrement it and return. And signal, there's no blocking, signal always just increments and returns, so there's no blocking. So the wait might block until it can finish the decrement and return. Okay, so that's the basics here. So this was, you often see in the literature, wait and signal are called P and V, which stand for the Dutch words. You can see the Dutch words down here. So this whole mechanism of semaphores, this data type, and it's used to synchronize communicating processes, to enforce precedence constraints, was invented by a guy named Edsger Dijkstra, very famous computer scientist, at, was it ETH? No, not ETH. Technical University at Eindhoven. I think that's where he was. I don't know, does Steve remember where he was? Anyway, no, Steve doesn't. Anyway, P and V. You see P and V. So in the literature, you can see P and V, and you can actually decide whether that means that you know that should mean wait and signal. Okay. So we have a pool of k resources. In the case of our n character buffer, we have a pool of n resources, which are the spaces in the buffer, is the number of characters in the buffer. So what we're going to do is there's this sort of notion of you have in shared memory, you have the semaphore, And then in each process, if you want to sort of use one of those k resources, you can go ahead and wait on it. And if there's one of them available, in other words, if the semaphore is greater than 0, you can decrement it, which means that you grabbed one of the k resources. So now the number out there is 1 less than it was because you've taken one. And you can use it. And when you're all done, you signal that you're done. So you wait until it's, you can use it. And then you signal when you're done. Right? And these two operations manipulate the value of the semaphore. Again, sort of, this is all, I'll show you a nice example now that'll show these things in use. So you think, so what is the value of the semaphore? It tells you the number of resources that are left in the pool. Right? If there's 5 laptops that can be checked out, everybody who wants to use a laptop does a wait on the laptop semaphore. And at that point, once wait returns, that means there is at least 1 laptop, maybe all the way up to 5 laptops in the pool. You get your laptop. The number of laptops in the pool gets decremented by 1, and you keep going. If you try to ask for a laptop, if you do a wait on the laptop semaphore and a 0, there's nothing for you to do. There's no laptop for you to use, no resource available. So in fact, you have to wait, and the wait will block until somebody somewhere else signals that a laptop has been returned to the pool, at which point your wait can now succeed. Okay. So we're going to use our bounded buffer problem here, use semaphores in our bounded buffer problem. We're going to use that to indicate the number of characters that are in the buffer. So initially the number of characters in the buffer is 0. And every time the producer produces a character, it will signal that there's another character in the buffer. So the resource we're managing is the number of characters available in our shared buffer. Similarly, the consumer is going to do the wait. So it's going to wait for a character. That makes sense, right? I mean, it waits for a character. So it's basically using the semaphores, checking that semaphore value. And when that semaphore value is greater than 0, it's going to say, aha, I'm going to consume one of them. So the wait will decrement the value of the semaphore, which is the number indicating the number of characters in the buffer, because I'm about ready to take a character out. Right? So this pretty much guarantees that the receiver can only receive characters that have been put into the buffer. So notice we put it into the buffer and then do the signal, meaning the character is already in the buffer. And then here we wait to see that the character is in the buffer, and then we take it out and consume with it. So does this solve our problem? Yes?
Wouldn't you want to take it out before you do the decrementing? Because otherwise...
No. In other words, you don't know... So basically, waiting to see that it's non-zero and decrementing happens as a single operation. And you'll see this is important because if we have multiple consumers and multiple producers, we will use this same scheme, and this will actually work fine. But it's important that both the waiting for it to be non-zero and decrementing happen, as an atomic, uninterruptible single operation. So wait is basically saying, not only am I going to wait for something to be available, but when I return to you, not only was it available, but you got it. All right, so wait combines both of those semantics. Is there something available, and can I have it, please? Wait does that in one atomic operation.
But then couldn't the producer stick a new character in between the wait and the C equals buff out?
Well, so one of the problems we might have here is that there's actually 2 precedence constraints we were interested in. One is that the consumer not consume a character that hadn't been produced, but you just mentioned the other constraint, which is what? What's the other thing we need to guarantee? I'm sorry? I'm not sure I understand. Say a few more. Well, that's guaranteed by the FIFO, in a sense, of the code. The code always is guaranteeing I'm taking them out in the same order they're put in. But there is a problem here. What happens if we keep running and running and running, right? What can go wrong? There's nothing in here that prevents the producer from producing too many. The consumer is guaranteed not to consume anything that's not there, but there's nothing in this code. So there's one precedent constraint, right? We wanted the ith receive to happen after the character had been sent. the ith character been sent. But now we have to make sure that the producer doesn't produce more than n ahead, right? Because otherwise the buffer will overflow. Right? And so the answer is, well, nothing prevents this from happening, and that's usually bad. Right? So it turns out that the semaphore was a great resource for dealing with making sure that the consumer only consumes after the producer is produced, but there's nothing that keeps the producer from overproducing. Right? So we have that precedence relationship that was established by the character semaphore. We need this one, which makes sure that the sender can't get too far ahead of the receiver. So we're going to introduce another semaphore that manages the space in the buffer. So the first semaphore managed the number of characters in the buffer. The second semaphore will manage the number of spaces in the buffer. Right? So when the consumer consumes a character, what does it produce? It produces a space. Right? Think of the producer as converting spaces into characters, and the consumer is turning characters back into spaces in the buffer. That makes sense? Right? And so it's the second semaphore that we'll use to implement the other precedence constraint. So initially, there are 0 characters in the buffer and n spaces. And what we're going to do is the producer now will have to wait for a space. And initially, if we start both of these programs running at once and the producer starts right away, what will happen? Will the wait on the space semaphore succeed, or will it block? It will succeed. Why will it succeed? Because space is initialized to n, so we basically can go around this loop how many times before it will stall, assuming the consumer is not running at all? N, right? After we've gone through n times, the space semaphore has been decremented down to 0. We've used up all n spaces. And after we've done that, what do we expect the character semaphore to be? N, right? So what do you think the sum of chars plus n should be at any given moment? N, right? We should completely account for the buffer. It'll be partly spaces and partly characters, right? So that's sort of the invariant here. And you can see that the way this sort of works is after we consumed a space, then we're going to produce a character, right? So there is a small gap in here occasionally where they don't at every specific moment exactly add to n. Okay, but after I consume a space, I'm going to produce a character. And so after I've run this punch of code here, that relationship is reestablished. And over here, I'm going to consume characters and produce spaces. So now we have both relationships. Okay, so it works with a single producer and consumer.